Hello viewers, welcome to our first episode on binomial theorem. Binomial theorem is a very significant result and you will be using it as long as you use polynomials in science or maths at higher levels. You are all familiar with algebraic identities. Algebraic identities as a plus b whole squared or a plus b whole cubed. You have all learned, practiced and used them in different forms from grade 8 to 10. Now, if I just ask you offhand, what would be a plus b whole to the power 5 or even 15? Will you be able to just write the expansion? I can guarantee that by the end of this lesson, you will be able to write that without any problem. So, let us get ready to introduce ourselves to the concept of binomial theorem and enjoy certain patterns that emerge along with that result. Start with thinking about what is a plus b whole to the power 0. That is nothing but 1, right? And a plus b whole to the power 1, a plus b whole squared, yes, a square plus 2ab plus b squared. A plus b whole cube, write down that expansion and now try to find out what is a plus b whole to the power 4. How would you get that? I have not talked about binomial theorem so far. So, obviously, you will depend on your previous knowledge, which would be simply taking a plus b whole cubed multiply with a plus b. Take a minute, expand and let us see if you get the same answer as I have here. On expanding and multiplying, you will get an expansion which turns out to be expansion with 5 terms. You will start with a to the power 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power 4. I think if you observe a little more closely, you will be able to see certain patterns, certain observations which you would agree exist, starting with the idea that total number of terms in each expansion is 1 more than the index. Index is the power to which the binomial is raised. Also the power of first quantity. In this expression, a is our first quantity, that goes on decreasing by 1, whereas the power of the second term, which is b, goes increasing by 1 in each successive term. What else do we observe? We observe that in each term, the sum of the indices of a and b is same and equals the index of a plus b. So, if you look at a plus b to the power 4 and if I pick the third term, which is 6a squared b squared, the total power, that is the sum of the power of a and b, turns out to be same as 4. Same thing you can see for each of the terms. So, definitely there is a certain pattern that is being followed here. Now, this pattern will be generalized and we will learn a few more things along with it, which will result in a result which we are going to term as binomial theorem. Now, for the time being, let us just focus on the coefficients of these expansions. If I only write the expansions coefficients of each term here, you will see that when the index was 0, I have of course only 1. When the index is 1, that is a plus b to the power 1 expansion, the coefficients are 1 and 1. So, I am going to write those coefficients down in a certain pattern. I want you to pick on that pattern and tell me what would be the coefficients when the index is 5. That is, when I expand a plus b to the power 5, what are the coefficients going to be? Are you able to guess? Definitely. The pattern suggests that the index when it is 5 will give rise to the coefficients as 1, 5, 10, 10, 5 and 1. So, how did you get this row now? I am sure you saw that when I take the coefficients of the index 1 and add them up in the order as in this diagram shown, I am getting that 2 in the middle term and 1 remains on the extremes. And similarly, when I take 1 and 2 together, it gives me that 3, 2 plus 1 adds up and gives me 3. And if I am arranging them in this pattern with the ones written on the side, which is now a triangular pattern, then the fifth index, that is the fifth power of a plus b, will give me an expansion where the coefficients are going to be 1, 5, that is 1 plus 4 coming down to 5, 4 plus 6 will turn to 10, 6 plus 4 again gives me 10, 4 plus 1 5, and then I put another 1. So, these are now the coefficients of the expansion a plus b to the power 5. What will be a plus b whole to the power 5? We saw two things earlier as well, that the power of the first term, which is a, reduces by 1 in each successive term, and the power of b increases by 1 in each successive term, and you already have the coefficients here. So, if you put these 2 and 2 together, I am sure you are ready to write a plus b raised to the power 5. It will look like a plus b whole to the power 5 as a to the power 5 plus 5 a to the power 4 b plus 10 a cubed b square plus 10 a square b cube plus 5 a b to the power 4 plus b to the power 5. Now, this arrangement that we just saw is an amazing expression which is known as a very famous result and a pattern known as Pascal's triangle. The name of course comes after the French mathematician Blaise Pascal. And as many other results, very significant patterns which have been identified and are very popularly known by French and other mathematicians, originated somewhere in our ancient history of India as well. And this result was identified by ancient Indian mathematician Pingla, and these are known as Meru Prastha as well. But commonly, everyone recognizes this pattern as Pascal's triangle. This Pascal's triangle has many more important and interesting facts. But let us now focus on the business of reaching a result which is known as binomial theorem. So, let us try to see the presence of combinations here, a concept that you just picked up in the previous chapter. We understand that yes, 1 can always be written as NC0 and also as NCN. So, I am going to use that to our advantage, and all the ones that we had marked on the two sides of that triangular pattern can always be selectively replaced as say 0C0 or a 1C0 and a 1C1, similarly 2C0 and a 2C2. But that 2 in the middle, that is in the third row, the second element, would always be replaced by 2C1 as well, because that is take the value 2. And now, if you are picking up the pattern, you will recognize and accept that each row in this Pascal's triangle represents a certain combination. So, I am looking at the third index, that is if the a plus b whole to the power 3 is being discussed, and I look at the coefficients in that expansion, then they do get related to 3C0, 3C1, 3C2 and then 3C3. Similarly, when the index is 5, the coefficients now look like 5C0 which was 1, 5C1 which is equaling 5, 5C2 equals 10, 5C3 also equals 10, 5C4 5 and a 5C5 which is 1. So, with this we are ready now to give rise to a result, putting this information together and of course, confirming the facts that if I have suppose the index is 7, the coefficients are 7C0, 7C1, 7C2 etc. I can use this general pattern and say that a plus b to the power 7 will be nothing but 7c0 a to the power 7. So, the first term starts with the highest power, which was the index 7, and each successive term the power of a gets reduced by 1, whereas b increases. And therefore, I ended up with that expansion a plus b to the power 7, which has now 8 terms, and each term is simply written by following the pattern. This is now an expansion of the binomial a plus b raised to the power 7, and with that we have our general result, which is known as the binomial theorem for positive integral index n. In grade 11 syllabus, you have only the binomial theorem for positive integral index n, whereas it is true for any rational number as well. So, right now we are going to talk about a plus b to the power n, where n is a positive integer, and therefore, the result says that whatever that n is, as long as it is a positive integer, a plus b to the power n can be written as nc0 a to the power n plus nc1 a to the power n minus 1 times b plus nc2 a to the power n minus 2 times b square plus so on. We will come back to that term in r in a while again, but how did we get that NCR a to the power n minus r b to the power r? Pattern, and the fact that the power of a is reducing, power of b is increasing, the sum of the powers of a and b always must be n. So, if I am writing this term, its position will be r plus 1. Also make a note of that, and we will come back to again understanding why it is r plus 1th term. And the last term would be NCN b to the power n, where of course NCR takes the value n factorial by n minus r factorial into r factorial. This is a very famous result which you will need and use for a long time. What we are going to look at is the same few facts that we have done earlier, but let us just try to put this theorem into practice. Now, I do not have a simple a plus b binomial. I am talking about expansion of x square minus 4 by x whole to the power 5. X not equal to 0, of course, is a condition given to make sure that this binomial does not become undefined. So, that is given to keep things defined, but focus is on expansion using binomial theorem. So, in this case, if I translate it in terms of binomial theorem result, then n is 5 and a is x square, b is negative 4 by x. So, I can write the expansion keeping in mind that I am going to end up with 6 terms, and the first term x square will reduce in power as I progress in successive terms, and the power of negative 4 by x will increase. So, if you just follow the theorem, you would be able to write the expansion and then some simplification, which would lead to a binomial expansion of the kind x square minus 4 by x whole to the power 5, ending up with these 6 terms, and that is what the purpose or the use as of now of binomial theorem is for you. Now, you can see that once you know the result, it is actually algebraic simplification. It takes a little while, but I am sure you will master it in no time. We will take up some more problems on the use and applications of binomial theorem in our next few lessons. Right now, let us focus on identifying and recognizing certain patterns in Pascal's triangle. Let us start focusing on this. Here I have a picture for you, and now you can easily see that there is presence of course, ones, And if I focus on the first diagonal, which is 1, 2, 3, 4, 5, 6, other than the first row, which is just 1, 1, 1, they are nothing but our natural numbers, counting numbers. And then the third diagonal represents the triangular numbers. Are you familiar with what triangular numbers are? Numbers as 1, 3, 6, 10, 15, 21. These are known as triangular numbers. These numbers are something which we are looking at as numbers that can be plotted, can be marked as triangular patterns. And the number of dots that are used to represent that number gives us the triangular number. So, if you look closely at this figure, you will be able to see what it means by triangular number. I have 1, 3 represented by 3 dots and therefore forming a triangle there. Then I have 6 which can be represented as a triangular figure, 10, 15 and so on. Also, there is a very interesting pattern that each of these triangular numbers can be generated and there is a general formula for it. You can always find the nth triangular number as n times n plus 1 by 2. So, if I am looking for the fifth triangular number, I put n as 5. So, 5 into 6 by 2 gives me 15. So, the fifth triangular number is 15 and therefore, you can find any other triangular number as well. More than that, what else do we have? Powers of 11 are present in each row of the Pascal's triangle. Isn't that amazing? 11 to the power 0 is 1, 11 to the power 1 is 11, 11 to the power 2, 121 and so on. As the number of rows increases, to identify this, you may need to figure out a little more trick, but as of now, it is a very obvious result. I will leave this for you to search for and figure out on your own. Another interesting fact is about Fibonacci numbers. Are you familiar with Fibonacci numbers? Fibonacci sequence is what you are able to find in Pascal's triangle. Here, take a look at this. You are able to see the marks that are showing. If I add 2 plus 1, I get 3, and then I am looking at the number 5 present. Then the next Fibonacci number, Fibonacci sequence suggests that other than the first two terms, which are 1 and 1, each successive term is sum of the preceding two terms. So, 3 is equal to 2 plus 1. The next Fibonacci number will be 3 plus 2, which is 5. So, you will be able to generate each of the terms of the Fibonacci sequence and you will see them present here in the Pascal's triangle. So, if I take 4 plus 3 plus 1, I get the next Fibonacci number, that is 8, and similarly as you go further down, you will be able to trace the next number, which is 13, 21 and so on. So, there is whole lot of information and patterns that are present in Fibonacci sequence. Powers of 2. Take a look at this figure, which is self-explanatory. You can see that if I add the terms of each row of this Pascal's triangle, you get powers of 2. So, the second row gives me of course 2, which is 2 to the power 1. Third row adds up to give me 4, 2 to the power 2. Then I have 8, which is 2 cube, 16, 2 to the power 4 and so on. So, there is a whole lot of world to explore as far as Pascal's triangle is concerned. It is a very interesting concept and I definitely would love if you can spend some more time on it, do some Google search perhaps and learn to identify these patterns. You will enjoy it. I will see you in our next lesson where we will be talking about more problems, applications where we will find binomial theorem to be a very useful result. See you then.